And Newton's universal law of gravitation has to do with how things orbit, how things are attracted to each other based on their force due to gravity between those two objects. I know we read just a little bit about that in that first assignment we did over our chapter, but we're going to get into it a little bit more today, and we're going to look at the gravitational force between two objects proportional to the radius, or how far they are apart, proportional to their mass, things like that. So this is kind of how he got to this whole notion of his universal law of gravitation. So his first thought and his first real question was, why is the moon kept in its circular orbit? Okay, what pulls the moon to stay in a circular orbit around the Earth? Why not an elliptical motion? Why in a particular path at all? Okay, because the moon does orbit the Earth in a circular pattern. It's not an elliptical. So once he kind of decided that was his question and what he wanted to really study, he started looking at the gravitational force between those two objects. Okay, how much force of gravity the Earth exerted on the moon as compared to the force due to gravity at the Earth's surface. Okay, what varied in those things? What made the difference between it, how far it was from the Earth or on the Earth's surface? Okay, or in other terms, the radius. Okay, how far something is from the center of the Earth, does it affect the force due to gravity? Was essentially what he was studying. Okay. So he knows that acceleration due to gravity at the Earth's surface is 9.8 meters per second squared. We know that. That's what we use all of our calculations. That's what we use in all of our calculations is 9.8 meters per second squared. And all of that acceleration goes toward the center of the circle, right? Toward the center of the Earth. So in this chapter in this lesson and then next lesson, Wednesdays, we're going to be able to calculate the acceleration due to gravity at different distances from the surface of the Earth. Okay? Because we know that once we get out into outer space, what happens to gravity? The force due to gravity increases or decreases? Decreases, right? Our acceleration due to gravity decreases. We have less of a pull from the Earth on our body as we get farther and farther away from the center of the Earth. Okay, yet on the surface we know that it's 9.8. So that's going to be Wednesday's lesson is going to be able to calculate the acceleration due to gravity at different distances from the center of the Earth. Today we're going to look more at the gravitational force between two objects. Okay. So he started looking at the masses of two objects, how they compare, the distance between them, how they compare, and he started looking at the force due to gravity. Okay, he reasoned that the force due to gravity must be proportional to both masses, mass of the Earth and mass of the object, using this equation. Okay, so he formulated this equation knowing that for an object on the Earth's surface, the mass of the Earth has to be one object, and the mass of the object is the second. The radius here, or r, is the distance between those two objects. So I'll go ahead and walk through what these subscripts, or what these variables are. Okay, F sub g is our gravitational force. Big G is a constant that I'll give you the value for here in just a second, but it's a constant. So big G value never changes. M1 is mass of object 1, M2 is mass of object 2. Usually one of these masses, it does not matter which one, is the mass of the Earth. Okay, if we are comparing an object's force due to gravity on the Earth. If we're looking at two separate objects, if we're looking at two people, then we'd have mass 1 equal the mass of the first person, mass 2 equal the mass of the second person, right? If we're just looking at the gravitational force between those two objects, we'll look at the mass of those two individual objects. Okay. So here is the value for G, for big G, 6.67 times 10 to the negative 11th. Make sure you can see that negative right here. Okay. 6.67 times 10 to the negative 11th. In this chapter, you do a lot of work with scientific notation in your calculator. A lot gets plugged into your calculator, and they're really, really big numbers or really, really small numbers. So I would really encourage you to use that E button for scientific notation if you don't do that already. Otherwise, you have to take an even more step of caution to put those parentheses in, things like that. But this chapter has a lot of places where error could happen in your calculator just by plugging in a number wrong or something like that. So you just need to be really careful when you're plugging these things into your calculator because they're pretty extensive numbers. This equation needs to go on your equation sheet. Okay, we'll use this one a lot. And you will also always get that G constant, so you can write the G constant on your equation sheet as well. Okay, I'll always give you G. It's not one that you'll have to memorize. All right, so let's walk through what our units would be here. Force due to gravity, what units would we have? Newtons, good. G is a constant, so we aren't really concerned with its units because it has every single unit in there that we need. Okay, M1 and M2, what do the masses need to be in? Kilograms, and R has to be in meters. Okay, because all of these units have to be accounted for. Newtons, meters, and kilograms. If we don't have our numbers in those correct units, that means our constant won't work. Okay, which means our equation won't work. So in order for our constant to work, we've got to have newtons, kilograms, and meters. Okay? All right. Here's Newton's universal law of gravitation, and it's word for word thing, so you do need to have this in your notes. So I'll give you a couple minutes to get this written down. So I want to talk about this last line right here. This force acts along the line joining the two particles. Okay? So I've got two people here on the center or on the surface of the earth, and let's say I want to find the gravitational force between those two objects, okay? Because Newton's law of gravitation tells us that every particle in the universe attracts every other particle. Okay, so at all times you're attracted to the objects around you. However, the mass of the earth is so substantial that that's what attracts you the most, so you stay grounded on the surface of the earth. You don't start sliding toward other objects, right? We don't randomly start seeing things start sliding and attracting to each other. Okay, that's because the force due to gravity between those objects is so small as compared to the force due to gravity the earth is exerting on that object, right? It's enough to keep us in place. However, if I do want to look at the force due to gravity between two objects, the path for our gravitational force doesn't go, to the earth and back. It acts in a straight line between those two. So the force acts along a line joining the two particles. So our force due to gravity between these two people would be a straight line, right? If the force was great enough to attract those two objects together, it would be in a straight line. Okay, like a magnet pulling to another magnet. They're not going to follow crazy paths to the earth and back. It's going to go in a straight line. So the force due to gravity between those two objects is the shortest distance we can find between those two objects. Okay, same thing if I was looking at the distance between a person and the earth, or the force due to gravity between a person and the earth. It's a straight line toward the center of the earth, right? The force due to gravity is pulling us straight down toward the center of the earth, a line joining the two particles. Okay, does that make sense? I know that seems pretty common sense, but all right, so I'll give you a couple seconds to get it written down. And we're going to try to solve for the gravitational force here. All right, so let's go ahead and start walking through our variables here. m sub 1 equals 50, m sub 2 equals 75. What does this value tell us right here? Radius. But what needs to happen to that 50 centimeters? 0.5 meters. It needs to be converted to meters, so we go 0.50 meters. Okay. What's the magnitude of the gravitational force each exerts on the other? So we've got a gravitational force value that's the same for each object. They're just exerting equal and opposite forces on each other. Okay, that's Newton's third law we're looking at here. So the gravitational force between them is equal. It just goes in opposite directions, right? One's pulling on the other with equal force that the first is pulling on the second. Okay, and what do we know that G is? 10 to the negative 11th. So we're going to go ahead and plug that into our equation here. All right, we're solving for our gravitational force. So this takes a lot of calculator work, and I'll kind of tell you how I do it because I keep the numbers in my calculator the whole entire time. Okay, so I usually start with the bottom right here, and I'll hit 0.5 squared. Then I'll take 50 times 75 divided by second answer. That way I keep everything in my calculator. Hit enter, then times 6.67, second E negative 11. Okay, I didn't have to punch any of those numbers into my calculator again. I kept everything in my calculator at one time so that I don't have to worry about rounding. I don't have to worry about punching something in wrong. It eliminates as much error as we can. But I got 1.00 times 10 to the negative 6 newtons. Force of gravity between two masses was 14 newtons when they were 10 meters apart. The distance between them changed, and the force became 56 newtons. How far apart were they then? Okay, so we want to look at the radius now of our second option when our force is equal to 56 newtons. So does something jump out at you here that we don't have? Yeah, we don't have mass, okay? But we can still do it, and I'll show you why. So get written down what you need to, and then we'll start going through this, how we solve for that. All right, it tells us for our first set of information here, we've got a force due to gravity of 14 newtons. We've got a radius of 10 meters. And we don't know either of our masses, okay? But our goal is to look at how far they are the second time when the force becomes larger. So if the force of gravity is becoming larger, what can you expect to happen to the radius? Gets larger or smaller? Smaller. They should get closer together, right? As our force due to gravity increases, the objects should get closer together. But we can't tell at what ratio that's gonna increase or decrease at this point. Okay? So we're gonna start plugging in some numbers here. We're gonna say 14 is equal to G, right? 6.67 times 10 to the negative 11th times M1, M2 over R squared. Okay? Will the value of M1 times M2 change between these two situations? No, right? So we don't care what the individual masses are. What we're going to do now is we're going to solve for M1 times M2 to get the total product of those masses, right? Because the masses aren't going to change between situation 1 and situation 2. So we have everything we can solve for, and we're going to solve for this basically as one variable. If you want to think of it just as m, that's fine. I'm going to leave it as m1 times m2, but we're going to solve for that basically term of our equation first. Okay? So mathematically, the way I go about this is I'm going to move my 6.67 times 10 to the negative 11th to the other side first. So I'm going to divide 14, 6.67 e negative 11th. Okay, when you divide by a number in scientific notation, you have to either put parentheses and use times 10, or you have to use the e button. Okay, so that gives me 2.09 times 10 to the 11th equals m1, m2 over 100. So times 100 times 100. And we're going to get our m1, m2 equal to 2.09 times 10 to the 13th. Okay, that's the product of our masses. We don't need to know individually what their mass is, right? They could be split evenly. One could weigh, 99% of that, and the other one could weigh the other 1%. It doesn't matter because the product of those two masses is still going to be 2.09 times 10 to the 13th for both situations. Okay, so now we're going to take our new force due to gravity and we're going to solve for the radius. Okay, because that's what we want to find out, how far apart they were. So I'm going to give myself some room here. (56) equals 6.67 times 10 to the negative 11th times 2.09 13th over r squared. Okay, so again, mathematically, I'm going to move 6.67 times 10 to the negative 11th over first. And get 8.4 times 10 to the 11th equals 2.09 times 10 to the 13th over r squared. Okay, so what can we do algebraically when our equation looks like this? We can switch these two places. Okay, which mean our equation looks like this. R squared equals 2.09 times 10 to the 13th over 8.4 times 10 to the 11th, not negative 11. So r squared equals 25. And we're going to take the square root of r and the square root of that to get our radius equal to 5 meters. So if we look at our radius compared to our first radius, what happened? It's half, okay? But what happened to our forces? Compare those two forces. Yeah, our force is 4 times as large, but our radius is only half, right? So there's a different proportion. They're not directly proportional to each other, okay? So we can't just automatically assume that since our force is 4 times as large, our radius is not 4 times as small, right? It doesn't have a direct correlation like that, okay? All right, so I'm going to give you a couple values here that you're going to use a lot. So this is asking us for the force due to gravity acting on a 2,000 kilogram spacecraft when it orbits 2 Earth's radii from the Earth's center. Okay, this r sub e is the radius of the Earth. This is really important. This is the distance from the center of the Earth to the Earth's surface. Okay, and that's really important stipulation for you to make, that this only goes from the core to the surface of the Earth. Okay, so if something is orbiting at a distance from the Earth's surface, we always would have to add that to the radius of the Earth, right? Because we want to know how far it is from the center of the Earth to that object. And then m sub e is the mass of the Earth. That's something that could go, these two values can both go on your equation sheet. I'll always give you those two values, but they're ones that are used often. So you can write those on your equation sheet if you want. Okay, 6.38 times 10 to the 6 meters for radius and 5.98 times 10 to the 24th kilograms for the mass. Bless you. Okay, so what this problem is telling us is here's our Earth here, our blue sphere. It tells us it's orbiting a distance 2 Earth radii from the center. That means 1 radii goes from the center to the surface, and it happens to be traveling the same distance from the Earth's surface. So essentially we have 2 radii worth of distance here. Okay, that's all that it's telling us. So we've got 1 radius that goes from the center to the surface, and again, it happens to be the same length of that radius from the surface to the object. So here's our orbital pathway out here. Okay, we want to find force due to gravity. We know that the radius is equal to 6.38 times 10 to the 6th. But how many of those do we have? How many distances of those do we have? We really have 2 of those distances. So we can just plug a 2 in, multiply that by. Mass of the Earth is equal to 5.98 times 10 to the 24th. And mass of our object, or M2, is 2,000 kilograms. All right, so now we can plug it into our equation. On the bottom, we have to be really careful that we square that entire radius. So if we're going to multiply it by 2 in our equation, we need to multiply it by 2 first, then you square it. Okay, the whole radius distance needs to be squared. So usually when I do these problems, again, I start down here, and I kind of work my way up into the left. So I'm going to start with taking 6.38 second e to the 6th times 2. Then I'm just going to hit squared because it's going to square my answer there without having to plug anything back in, and hit enter. Then I'll take my 5.98 times 10 to the 24th times 2,000 divided by second answer. I can take that whole thing times 6.67 times 10 to the negative 11th. And I get my newtons. So again, I start with this term here, then I square it. I take this divided by that denominator, then I multiply that whole answer by 6.67 times 10 to the negative 11. So never did I have to re-plug in a number into my calculator. I always use the answer. Okay? You know, if you have an answer in your calculator and you just hit times, it automatically takes that answer times whatever you're going to do next. All right, what's the net force on the moon due to gravitational attraction from both the Earth and the sun? Okay, we're going to see basically which of those is pulling the moon with greater force, where it's going in comparison to both of these objects. So this is going to be a little bit two-dimensional, but it's pretty simply two-dimensional. Okay, we're going to assume both the Earth and the sun are at right angles to the moon. So I'm going to put some information out here first, and then I'm going to draw our, and then I'm going to draw what it looks like. Okay, so here's our sun, our Earth, and our moon. Okay, these are both at right angles to each other, so, or these are at right angles compared to each other. Okay, M sub m is mass of the moon, M sub e is mass of the Earth, M sub s mass of the sun, and then it gives both of our radius. So we're going to solve for each of these gravitational forces separately, and then we're going to be able to just do vector addition. So we're going to be able to solve for the resultant, basically, of those two force vectors. Okay? Once we've got these, right now they're not added tail to tip, but this is essentially a gravitational force vector. This is essentially a force vector. So once we've calculated each of these force vectors, these gravitational force between these objects individually, we're going to be able to add those vectors tail to tip and find the resultant to give our overall gravitational force. Okay, does that kind of make sense? Maybe? So let's go ahead and find F sub g between the Earth and the Moon first. Okay, so we're finding the gravitational force between these two objects first. So we're going to say F sub g is equal to big G mass of the Earth times mass of the Moon, so 5.98 times 10 to the 24th times the mass of the Moon, which is 7.35 times 10 to the 22nd, over the distance between those two objects squared. We square that whole term. Okay, so force of gravity between the Sun and the Moon. I'm going to plug in the mass of the Earth times the mass, I'm sorry, not the mass of the Earth, that was, no. Mass of the Sun times the mass of the Moon over the distance between them squared. All right, and what do we get for F sub g? I got 4.34 times 10 to the 20th. Yeah? Okay. The tip. Okay, so we're going to take our gravitational force on the Sun and our gravitational force between the Moon and the Earth. We're going to add the vectors tail to tip, and we're going to get the overall resultant here. So we find out with what force is it truly being pulled and at what angle. Okay, so here's just simple Pythagorean theorem. And I got my resultant to equal 4.77 times 10 to the 20th newtons at, we want that angle also, so we're going to use second tangent. (65 degrees), and in this particular drawing it is blank of blank. What is it? East of south. What axes is it touching? Right, if here's our origin, what axes is it touching? The south axis. Then we decide, is it going east of south or west of south? Okay, and it's going east of south. Okay.